So I am a groundwater hydrologist. I'm not a hydrogeologist because I'm not really a geologist. And that there's a distinction there in that you do different coursework, and I'm not a licensed geologist, but if you want to work in the environmental business, it's a good idea to get either a professional engineering PE or be a professional geologist, because it turned out that after I graduated from college and did my studies, that those people got a hold of the regulators and said, yeah, we need to be able to sign off on this. And I was registered with two national organizations, the American Institute of Hydrology as a groundwater hydrologist, and also the National Water Well Association of groundwater scientists and engineers, and so I have a national registration, but it's good for, I guess it's good for putting behind your name, but in terms of putting out your own shingle and doing stuff, it's not as accepted nationally as a person who can sign off on designs and reports and things like that. But if you're going to be a scientist or an academician, it's probably more appropriate. So I come to you from University of Vermont, bachelor's degree in soil science and geology, and a master's degree from the University of Arizona in groundwater hydrology. And that's an engineering degree. I started work, I probably left grad school too early. I wish I would have stayed now, but I was hounded by Bechtel International Corporation. They said, we want you to work first, you want to work first, we want you to work for us. So I left before I'd finished my master's thesis, and I did it while I was working there, but turned out that they had a very important project, and the important project was the waste isolation pilot plant. And they needed a groundwater hydrologist to interpret the data and to produce what they call a safety analysis report. And so here I am, my first day on the job, and they're saying, hey, we want you to do this, and you're going to analyze all the data. And I'm like, well, okay, all right, bring it on. Let's get started. Anyway, the final denouement of this is that the WIP got licensed, and it's still working today, and it's protective. And a couple of things that I kind of chuckle about is, they had this Yucca Mountain, which was also supposed to be a nuclear waste repository, and they didn't get it licensed. And two things that come to mind is, well, the WIP was buried 3,000 feet down in the ground in buried salt, and those heavy isotopes aren't going to come back to the surface by any means, and the way that they could have had exposure was by erosion of a canyon with the Pecos River, which was estimated to take several million years. And when they asked, is there any probability that happened, I said no. And so people accepted that. When they went to do Yucca Mountain, they did probabilistic modeling, which made them say that yes, there's some probability, even if it's very finite, that it could escape. And they called the repository a mountain, and so people pictured it being above the Earth's surface, and just a bad idea altogether. So me one, the rest of the regulators and scientific community none. I won anyway. I got on the scoreboard. So after that, I had a career with the Bechtel licensing nuclear power plants, doing the safety analysis reports, and then 3 Mile Island happened. And so they said, okay, Kent, we want you to go there and design a groundwater monitoring system for the containment structure. That all the radioactive waste had gone into a kind of a basement of a building, and they're worried about that building would leak and that the stuff would get into the Susquehanna River. So sure enough, designed the system for that, and I got a lot of criticism from some engineers. and nothing bad about engineers, but they're not always experts in groundwater, and so they couldn't understand why some ground contaminants could move ahead of the average seepage velocity. And if you look at a groundwater system with a porosity, there's different lengths of flow paths, and water travels at different rates depending on the dispersive properties. Some moves ahead of that average seepage velocity, some moves behind. And so they got this expert, Papadopoulos. He was he has a couple books out and stuff like that. And they checked my calculations, and sure enough, I was right that the contaminant would get to the river ahead of the average seepage velocity. So that was kind of an exercise in these things where, if you know your stuff and you stand by what you know is right, and you can listen to other people's criticisms, but know your stuff and stick to it. That's kind of my advice in these cases. So anyway, after that, I went and I worked for the Department of Energy, doing design for tailings of uranium that were associated with the milling process that produced yellow cake. And I did that for a while, and then I became a consultant for the EPA, and I reviewed pump and treat modeling simulations for different sites throughout the Region 6, that's Texas, Arkansas, the New Mexico, that area. And then finally I got moved to Oak Ridge, where I worked on remediation of nuclear sites for the DOE. And then after that, my career got difficulty and it came in difficulty, and I had a lot of job changes because of age discrimination. And we'll talk a little bit about utilization and billability as a consultancy. After this conference, you may decide that, well, I want to stay with a public agency in some place that gives retirement. But anyway, I'm also going to talk a little bit about how to get a job with a consulting company, a private consulting company, if you want one. You may decide, make some kind of decision otherwise afterwards. So let's get started here. These are the subjects that we're going to talk about, and sampling and site work. That's generally a place where you will get your first job with a bachelor's degree and a master's degree. We're going to talk about modeling. There's two types of modeling. There's visualization modeling, which was that picture that we first showed up before they put the topic slide on. And that is non-predictive. And then there's the modeling, which is also predictive, which basically tells how contaminants move through a groundwater, from the vadose zone through the groundwater system to a point of exposure, and why that's important. We're also going to talk about various types of contaminants. We'll talk about PFAS, which is the contaminant that you've probably heard. It's a very prescient issue at a lot of sites. And then we'll talk about basically groundwater resource development and how to use the tools of the profession to demonstrate compliance with the regulations. So we'll start off with water sampling, because that's probably everybody I know is probably thinking about their first job. And so kind of the idea of this is to just give you an overview so you know what water sampling is like, you know the terms, and if you're in a job interview and somebody says, do you know about low flow sampling? You can say, yes, I attended a class on that, even if it was only an hour. So low flow sampling, why low flow sampling? And why is it important? Well, under traditional purging over here, let's see, there we go. It was usually considered a 3-volume pumping of removal of the casing volume. And the idea with that was to get stagnant water out of the casing and get formation water to come in like this. But it was basically at a high volume, high rate. And when we say high stress, that means that the velocities coming through the well screen are quite high, and you get turbidity. And why is turbidity a problem? Well, turbidity has its particulate and can be very small particulates. You know, it's basically cloudy water. And the problem with that is that those are typically clay sediments or organic sediments that have a high cation exchange capacity. And if you're sampling for metals, a lot of metals are cations, or they form cationic complexes, and so then they wind up in your sample. Now, originally this wasn't a problem because, you know, state agency says, well, we'll allow you to filter sample. By filtering a sample, you put it through a 0.45 micron, and it pulls out the particulates. So there's a very different, when you don't take a filter sample, it's called a total sample. And so they're saying, well, the state agencies will say, well, you know, you're not going to have a filter at your sink, and you could potentially drink this stuff. And so they applied total samples to the standards. So now you have to comply with total water samples. So what that means is that if you have a poor performing well or a poor sampling method, you can have false positives in your detections of metals and other constituents that we're regulating. So in the 90s, the EPA came up with this thing called low flow purging. And the idea is that you purge at less than 500 milliliters per minute, and that you don't create a lot of drawdown. You don't want more than 0.3 feet of drawdown. Drawdown is the difference between the static water level and where you are during pumping. And so what happens is that to show that this is low flow pumping, they force you to take a water level and a turbidity reading and what they call stabilization parameters at 3 to 5 minute intervals. And when the well has stabilized, then you can take the sample. And so that assures that kind of the idea here is that the stagnant water sits in the well casing, and you're getting the water that's flowing through the well screen, which is down there. So what are the instruments involved? Okay. This right here is called, wrong button. Okay, this is what they call a sonde, okay? And it's a flow-through cell. Now, you'd say, well, why would you sample through a sonde? And say there's a bladder pump which is in this well, and the water comes out like that, and it goes through the bottom of the sonde, and this is fully saturated, and then it comes out here. And this basically has this thing called a sonde, and that sonde has an EC meter in it, a pH meter, ORP meter, and a DO meter. And so you're as the water comes out, it's going in this cell, and this cell prevents oxygen from getting to it. And that's very important because if the water gets oxygenated, it can change the pH or the ORP, which is oxidation reduction potential. So this is a turbidity meter. You take a little glass vial and you put it in there every 5 minutes, and you read it on here. And normally the turbidity is supposed to be below 5 nephelometric units, which assures that the water is clean. You can see all this plastic around here like that. Okay, that's to keep the table clean, and you change gloves every time you do a procedure or go to a different well. And this is a sampling stand. So when you take the sample, they're going to disconnect this tubing from the well, okay, and then they're going to sample from this tube, okay, through here at the same rate as what they got when they were taking the sonde measurements. So this is what stabilization looks like. And you can see that here are the parameters. So there they are. You got temperature, pH, DO, turbidity, electrical conductivity, and that's ORP. So they change, and then finally you reach this point where they vary by very little, and then you're allowed to take your sample. Now, how do sampling methods affect the results? Okay, here's this chart here may look like a bunch of lines, but it's the conclusions are actually quite profound. So I was at a landfill in Pennsylvania, and they said, "Oh, we have a mercury problem. We have a mercury problem. Help, tell us." And it was rumored that sometime, this is like typical landfills, somebody buried some industrial mercury waste, and they were seeing it in the water. And so these are different sampling measurements of ways to do in other words, we tested the wells by different sampling methods. So this one here, the gray one, okay, that's a Baylor sample, okay? And here's the standard for mercury down here, 0.1, okay? So you can see this one here is a skyrocket, it's like maybe 100 times the standard. This is 10 times the standard, 12 times, and so very bad method. And they did have low yield wells they're sampling with Baylors. Typically when a well goes dry, they sample with Baylors. Why is that bad? Well, it's because, they go down and they hit the bottom of the well with a Baylor, and it stirs up all the sediment. There's usually like a sump in the bottom of the well below the well screen. And so that sediment is then in the water sample. They take it up. It's a total sample that goes to the laboratory, and all the metals that are absorbed to the clay and particulate matter that were in that sample get analyzed, and they have this exceedance. So the next method was 3-volume purge, okay, and that's the black one. And see, they have these exceedances and a very big one there. Not so hot. So then they had, okay, let's do, and that was, okay, here's a low flow dissolved mercury, okay, and that's they only had really 2 hits. So the black one is the 3-volume period. This is dissolved. So that was better if they had low flow with taking a total sample. This is the best though if you can actually filter it and get the sample without disturbing the water column as much as possible. So then the recommendation for this was, well, your wells are bad. When was the last time you rehabilitated a well? And we'll show you what well rehabilitation looks like. There we go. So here, this is what I call a proclivity chart. And this is an example of a TVA well, okay, Tennessee Valley Authority. And I work for them as an auditor and as an analyst for looking at water quality types. Everything over here, see, this is, these are total constituents, and these are dissolved constituents. And you can see how they have these exceedance of the groundwater standard for cobalt, arsenic, and the exceedances are much worse when you have a total sample. And so what are the things that are causing this? Well, if you have low DO and negative ORP, or ORP is fluctuating from positive to negative, that means that basically you're mobilizing contaminants that maybe wouldn't be there if the well was in a different place. And kind of you can look at let's say fly ash. This is for fly ash, okay, at a TVA site. And if you look at fly ash, they basically put them on top of swamps. Because if, the plant is next to the river because they need the water for cooling. And so they find this low spot and they go, okay, well, we're going to have gravity feed that takes the fly ash by a slurry and puts it in this pond. And so the fly ash basically settles out, but there's enough organics in it that it manipulates the pH and the ORP so that it's mobilizing metals from the underlying peat that they built the thing on. And so it's like, I said, I can get rid of all your exceedances if you just move your wells outside this envelope of ORP where these things are soluble. And as soon as you get outside that, you get back to a neutral pH and a positive ORP, the contaminants all go away. They can't migrate because they precipitate. And they go, no, we want to spend $2 billion and take it to Alabama. That's what they're going to do with the fly ash. And I go, you can leave it in place. But, they had this regulatory idea that we're going to go to Alabama, and they didn't care that all this money was going to get billed to the utility users. So, go figure. Okay, this is well rehabilitation in practice. Okay, so you can see here's the Clinch River. You may have heard of the Kingston fly ash spill. This is that site, okay? And so they're putting in monitoring wells, but they're putting the monitoring wells through the dike so that they're still in this envelope of low pH, low ORP that's causing the contaminants to be mobile. And this is what they call this is a surge block. And so they have this mechanical arm that moves up and down the well on this pipe, and it pushes this surge block up and down. And you move this thing up the well like this and down the well like that, the well screen, until the water reaches the turbidity standard of 5 nephelometric units. So if you want to get good wells, you have to do that about once a year. And so my site in Pennsylvania, I said, when was the last time you rehabilitated your wells? And they go, rehabilitation? What's that? So these are the kinds of questions that a consultant asks to make themselves useful, and it's all kind of about the quality of the data. These perceived exceedances and people throwing up their arms. What are we going to do? What are we going to do? Let's make sure that the data is good first. And kind of my thought is when you go to these sites, you use a thing called adaptive reasoning. And what the adaptive reasoning is that it's that you look at all the existing information and you make a conceptual site model. But that conceptual model may change with time as you get different information, So the different information was, in this case, was, have you rehabilitated the well? How did you sample it? Okay, was it a dissolved sample? Was it a total sample? Those kinds of things matter to keep in your mind when you're evaluating data, because the exceedance may be a false positive, and you do your client a great service if you can tell them that is the case. Okay, let's talk a little bit about uranium tailings. Now, this is a very interesting site. Way back in the day, I was a regulator. It was my second job out of college. I worked for the New Mexico Environmental Department, and right here was a tailings pile. And this is in Ambrosia Lake, okay, in New Mexico. It's 70 miles west of Albuquerque, and they had this Ambrosia Lake Valley. There is no lake, but maybe it was a progrglacial lake or something like that, something that happened way back when the Indians were there. But this is the Grants Uranium District, and basically there's a creek that comes down from here and flows by the tailings like that, and then comes down here and out like that. This is a high spot where this is an alluvial aquifer, okay? It's about maybe 200 feet thick, and it overlies the Chinle. And so when most of these sites have evaporation ponds, because when they basically grind tailings to a fine grain, and then then they attack it either with a very low acidic solution or a very alkaline solution, and that's to get the uranium in solution. And then they precipitate it and form yellow cake. Okay, so I used to have to regulate this site, and the regulators always said, "Oh, let's take you to the mill, take you to the mill." And I go, "Well, okay." And then they had this room, and it's like they have these drums, and they go, "This is where we pack the yellow cake." And I'm like, "Yeah, okay." All right, okay, yeah, I see it. Get out of there quick. But the reason why they didn't have evaporation ponds is because they put this tailings pile over permeable alluvium, and so kind of the tailings have the center is like, it's like a jelly donut. The outside is sand, a sand berm that has a phreatic surface in it, and the inside's just like this lime that, if you drove a truck over the banking or whatever, you could see it shake. So the middle of the stuff is low permeability. The outside is permeable so that the phreatic surface weeps out of the pile and it doesn't get too high and influence the stability. But they have had some of those slide, and the reason for that is because they liquefy if the dam breaks, and that's one of the reasons why the fly ash dam at Tennessee at Kingston broke, is because it liquefied. So they have a uranium and a molybdenum and a selenium issue here, and they're worrying about how they encourage people to settle here, and basically the contaminants moved and contaminated all the shallow groundwater there as a source. So the question was, okay, how do we fix that? So here's a useful geochemical tool. This is called a Tessier extraction analysis. And here we're looking at some borings where these samples were taken. And so for instance, in this case, we'll look at molybdenum. And so these are the different extractions here. So in this progressive extraction, you're going to look and see, okay, the blue is what's soluble. The next one down is what's absorbed, the green. The red is iron manganese oxide borne, and green is organic sulfide borne, and the black down here is residual. So, for instance, the typical thing is people say, "Oh, look, this thing's leaking," and so that all the contaminants are in this phase. And so when the DOE licensed these for long-term management, they had a groundwater model, and in the groundwater model, they assumed that all the contaminants were in this phase. And the idea behind that was that the regulations said that if you can show that in natural flushing, the thing that the groundwater cleaned up, you didn't have to do any more remediation. You didn't have to do groundwater remediation, and the cover that was on the pile was probably fine. Well, it turns out that none of these sites ever were even proceeding towards compliance. In fact, what happened is that because it turns out that most of the contaminants were in this phase and they were continuing to dissolve, and that basically when this raffinate, which is what was the spent solution that came out of the mill, was discharged to these ponds. These ponds are online. Okay, these tailings were online. That stuff went down into the groundwater system and it got buffered. Well, what happens to a low pH or high pH water when it gets neutralized is all the contaminants form minerals in the subsurface, and so those minerals continue to redissolve. And so initially, like the owners of the uranium mills were very smart. They said, well, we're going to put uranium at 5 milligrams per liter, and that was about the solubility of uranium with these minerals, and when it was in contact with these minerals. And so what happened is then the EPA comes along and says, oh, we're going to put the standard down to 0.44 milligrams per liter, which you could never be in compliance with this amount of mineralization in the subsurface. It just wouldn't work. So that also put all these sites out of compliance with long-term management goals. So, 30 years later, after my first job, first or second job working on this stuff, I went out there and they said, help, we're not making the standards. And so, we're looking, well, let's see if we can optimize what you got here. So this is the 100-year plume limit for migration. And so we said, well, we'll look at the wells here, and you can see that, there's this flow path. This comes out here like this, and this high spot here where the groundwater, there's no groundwater, basically acts as kind of a barrier. And so a lot of these wells were redundant. So we just took a few of them that were along the flow path and said, yeah, we can get rid of all those. We'll reduce your monitoring burden. And then here's I call this the wells with proclivity table. And so we said, we'll rank the wells and get rid of all the bad wells that you don't need for long-term monitoring. And so, pH less than 6 was bad. Wells with steel casing, we don't like that. For low flow sampling, we don't like wells with 2-inch diameter, basically, because if you're sampling, you're blocking the well screen with your pump. Screen length, we don't like less than 10 feet, too much drawdown. ORP fluctuations, bad, as we said before. Well and tailings, that's a no-no because you can't guarantee a seal. And then specific conductance, this shows that if that's really high, you're probably monitoring waste. And we want to monitor groundwater. Then, we're looking at the design of, the life of a well. And that's really about 30 years. So, if your well's 30 years old, there's no sense in keeping it. Low transmissivity, you're probably getting excessive drawdown, so you want to get rid of that. And then, these were basically, if they're outside the future plume, we didn't want to keep monitoring a well now if the plume's not going to be there for 100 years. So we optimize their system doing that. And, you're going to have, this is one way you can do that. Like all these people, some of these sites have 1,000 wells, and it's prohibitive to sample them all. So, you need some kind of justification to the regulators because, they think everyone's a treasure, but actually some of them are providing bad information. So this is it's back to this thing about sampling. Make sure your wells are producing accurate or representative information. So now we're going to move on to some more current stuff. Right now I'm a consultant with Aerostar, and they have a bunch of sites in Michigan that are former Air Force bases. And so the contaminant of concern there is PFAS. And so PFAS, we're going to have a little bit of elocution exercise here. It comes from aqueous film-forming foams. Everybody say that. Aqueous film-forming foams. Okay. All right. And PFAS is per- and perfluorinated alkyl substances. Okay? And so say that. All right, we'll skip that. But anyway, kind of the idea, these are 8-chain carbon fluoride molecules. And they are what they call amphiphilic. And by that, they have two charges. There's a negative charge that likes to stick its tail above the water table. And they have a positive charge that is ionic and has its head down in the water table. And they're basically, they call them, forever chemicals, and that's because they don't degrade in the environment. And so why they are there is we can look at a couple of sources here, but the main one at an Air Force base, the highest concentrations are typically associated with firefighting pits. And the history of these pits is that they went out and put solvents and fuels in the pits, and then they go out and put them out with either water or aqueous film forming foams. And so these things are in these pits and they form a source. And then there's other spots where, you know, this is like a flight line at the Air Force Base, and there's, you know, places where planes crashed or they had fires. And then there's basically maintenance yards and fuel storage areas. The main constituents of these things are PFOA, PFOS, PFNA, and PFHXS. Okay, and so those are the short names for perfluorinated sulfonic acid. Okay, so that's PFOS, for example. Why this is important, okay, is this shows basically how stuff moves here. And we have a little movie. We all like movies, right? So I'm going to play this little movie. And this is not a predictive model. This is just it's a visualization model done in Leapfrog. Leapfrog is a 3D dimensional tool. And so what this is showing is it's showing how there's this geology here that basically controls the movement of groundwater in the valleys. And so we're basically slicing the plume at different depths. And so we can take a look at this visualization model. Okay, the blue lines here are groundwater flow equipotentials. So, you know, there's flow in this direction, there's flow in this direction down here, and there's some flow that's back in this direction. So there are some exceedances over here, some hits, and people were saying, well, you know, we have property issues here. We weren't able to get across the property here to sample. So the question was, well, how do we know that this is related to this? Do we really know that? But the other thing about this site, okay, this surface here that you're looking at, those are the low points. You know, the gray is the bedrock surface. So basically, there's alluvium sitting on a bedrock surface, and there's two wells here, and the question was, well, if we pump from these wells, is that going to, you know, connect to this? And because, you know, basically it can't. It's almost like there's a boundary there because it's in the wells are sunk deep into these gullies here. Also, if you notice the previous contractor said that, you know, these things were erosional features, but because they're so geometrically oriented, I think that they're associated with fracturing in the geology and then dissolution rather than erosion, because, you know, the valleys aren't continuous. You can't get you know, it's not like an erosional feature. And so this is what we're doing. Basically, there's this creek here, and they're worried about discharge to the creek, and that's another issue. Michigan has these things called groundwater surface water interaction regulations, and you have to put in special wells to see if this stuff is discharging there, and if it is, then you have to write a report. So this particular contaminant is PFOS, and it's probably hard for you to see the concentrations, but the PFOS standard now for these sites is 4 parts per trillion. Okay, so we used to worry about solvents in the micrograms per liter range. Now we're in the parts per trillion range, so 1,000 times lower concentrations. And that presents a whole lot of trouble for sampling because, you know, just if the cross-contamination is, you know, it's 1,000 times, the standard's 1,000 times lower. And, you know, they were worried about cross-contamination with solvents. and we're 1,000 times lower. So all this business about having plastic on the table, you know, changing gloves, not, you know, if a bottle ground falls, throwing it out, and so forth. All that's very important and an important consideration in looking at data quality. So here, this is some more of our tools where, and we can, when we're doing our analysis, we can lay cross sections now across what the plume was you saw before. And so the question is here is this one or two aquifers? You know, there's an aquifer up here, there's a water table there, and then there's these like clay layers here, and then there's this down here. And this is where they put the city wells. So the question is you know, is this aquitard going to be sufficient to prevent the PFAS from getting there? And it turned out that they did a groundwater model, and they decided that if they pumped at a reduced rate,
10 minutes.
10 minutes? Yeah. All right, okay. If they pumped at a reduced rate, that the stuff wouldn't get there, and so they put a sentinel well in there. So we're going to get to the end. So this is excuse me. This is a technique here that shows how you would look at the various PFAS components and whether or not that plume that we saw that was way off to the east are all related, and it looks like they are because they all maintain roughly the same concentration but in lesser degrees moving along the flow path. So here's what, this is at another base where a plume flows into a lake, and they were doing two-dimensional mapping, but if you go back to look like this is what was done in Leapfrog. You can see that most of the contamination in red is at the top of the groundwater, and it's related to how PFAS, partitions in the soil, and it stays at the water surface because of that amphiphilic tendency. So this is the two-dimensional shot of a plume I'm going to show you and then I'm going to show you the remedial design. And here's the remedial design, and this is what was originally proposed as a capture zone. And there's a problem with this in that you can see that this well is going to pump clean water until it pumps this water. And so basically they wanted to stop this from going into the lake, but it's a bad idea because basically you're pulling this water through a larger volume and you're actually contaminating more water. This is what they call particle tracking modeling, and it was one of the reasons why a lot of pump and treat systems failed. So if you look at this is the cross section through the plume, you can also show that the source here is not connected to this by low concentration. So if you're putting all your pumping wells here, you know, if this is already disconnected, this is never going to get to there. So you want your wells to be in the center of mass when you're pumping. It's like, in a very simple analogy, I call it pin the tail on the donkey, which is, you know, you don't want to put the pin over here if the tail's over here, right? So here's an example of inline plumes with particle tracking and how you can capture this mass and not pull extra clean water into the well. You know, that you basically line your wells along the axis of the plume. So transducers, okay. I understood that somebody just went through a symposium with USGS with transducers, and this is what looks like putting a transducer in a four multi-completion well, and they have optical readers, and this is what a transducer graph looks like. And this transducer graph was produced to interpret where we saw those two wells that were out there in that low spot to see if they were responding to monitoring wells were responding to that pumping, and the pumping is basically shown by these triangles, and the the question was, well, is this confined groundwater, is it not? And because these if you look at those undulations that are going like this, it turns out that that's the response of a confined aquifer because it's responding to barometric pressure. The barometric pressure is weighing on the confining zone and causing a diurnal fluctuation. So that right there, that one transducer in the well answered the question that probably 30 wells and borings would not. So here's another tool that we'll get to. It's a Piper diagram, and the Piper diagram can be used for distinguishing contaminated water from the background. In this case, this is a calcium bicarbonate water, and this is the background, and these are the contaminated zones that have a higher sulfate, and higher chloride. And so it's very important to account for, in a Piper diagram, what you're doing is you're taking the anions and you're converting them to milliequivalents, which is dividing by the valence. And so then you're plotting them along the axes as percentage of the total, okay? And so you have to get a general chemistry analysis to do this, but it's a very, very important tool. So either call them Piper diagrams or trilinear diagrams. Generally, the one that's down here is called trilinear, but if you consider the whole thing together, it's a Piper diagram. So this is just another example of we're looking at groundwater flow along potentiometric contours. These are equipotentials in this direction, and everybody said, oh, groundwater's flow there towards the Green River. But it turns out that, lo and behold, that there was basically a pile that had iron coal that couldn't go through the plant, and so that iron coal basically oxidized and produced acid mine drainage and caused this plume to flow this way, and they're attributing it all to this pile, which was actually properly constructed, not leaking. So here's another example of water quality in action. This is a example of the Allen power plant in Memphis. And here the river's flowing inland during high water stage. And how did that affect chemistry? Okay, well, arsenic absorbs to iron that's oxidized. That's this field. This is EH versus pH. They call it EH pH diagrams. And so this is a tool that chemists use. But then arsenic is released when it's in this phase here, the reduced iron. And so, for instance, when water levels come inland, we see that the ORP goes way up, which means it's oxygenating. So that affects the arsenic. So the arsenic follows the ORP. And it turned out that this was not a constant feature, that it was changing all the time, and that perhaps it wasn't related to the pollution coming from the fly ash. It was from what was in the aquifer underneath it. So here's another tailing story. And this one's very important because it illustrates how you look at things, how you stand up for what you know is right, and how you can save a lot of money to people that don't understand what's going on. So here's a typical radon barrier at Shiprock. And it's basically a monolithic barrier, 7 feet thick clay with riprap on it. And this was designed for arid regions, and so the originally there weren't groundwater standards for the uranium mill tailings reclamation project, and they came up with this idea. Well, let's have a groundwater standard, and they'll have to comply with it. So the Department of Energy was very worried because they didn't know if these piles and covers would comply with the new groundwater standards. So they set this thing, well, 10 to the minus 7th is impermeable. It's 10 to the minus 7 centimeters per second. So if we can get a pile that can comply with that, we're going to meet the standards. And so there was people that were modeling, and they said, oh, well, these covers saturate with time. And here's the cover. You can see that there's the tailings down here, and then there's some kind of material that was windblown stuff they put on it, and then there's the thick radon barrier. And I said, well, these things, if we can show that these things operated in an unsaturated fashion, we could get the standards, and we wouldn't have to retrofit all these things with a liner, which would cost millions and millions of dollars. So we went out and implemented the radon barrier with tensiometers, lysimeters, and so forth, and took borings. And we found out that the vertical moisture content was not changing in the radon barrier, and soil tension, which is called suction, and was invariable at depth. It fluctuated a little bit in the top. So what did that mean? Well, if you consider the fact that the gradient through tailings you have the gravitational gradient, which is 1, and if you don't have any change in soil tension, then your overall gradient is 1. So your vertical flow rate is whatever the percent saturation is at that conductivity. And the pile operated unsaturated because we're less than 100%. So if you come over here, it shows that the cover was 10 to the minus 9th for that unsaturated cover, and it turned out that monolithic clay radon barrier was good. So we were 2 orders of magnitude below 10 to the minus 7 centimeters per second. So this was one of the first ET covers that was ever built, and we saved the Department of Energy from having to redo covers on 20 sites, which is huge, And so just using, some good hydrology, they agreed to it. And that was a big win. So last set of slides here. Okay, so we talked a little bit about 3D visualization, and now I'm going to talk a little bit about give me 3 more minutes. This is fracking, okay? The nice word, and the problems with fracking is they have this thing they call it stray gas migration or stray gas forensics. And so the question is where did the gas come from? And whose fault is it? So this is what a gas well looks like, and here are all the formations that it goes through, but basically, we're in Pennsylvania in this case, and the gas is coming from the Marcellus Formation. And I can tell you that there's 0 chances of the gas coming up from the Marcellus Formation. But what we do have is there's all these intermediate formations here that have some kind of gas in them. And so that gas changes isotopically due to the thermogenic properties of the formation, how long, the shallower it is, these isotopic ratios change. This is delta deuterium versus that in SHMO, and this is carbon-13 versus PD velmite. So this is what they call a shoal plot. And you look at this, and so you can tell, how he showed all those stringers, you can actually show what part of the casing is leaking by looking at this plot. And so then they have to go back and fix the casing, and they shoot it and they put more cement behind it. And you might think that these things are cemented all the way down. Well, somehow they managed to cheat and not do it. but the good news is that it's well regulated by the Pennsylvania Department of the Environment. And really, if they can't fix the well, then they buy your property. So here's an example of that same plot for the Marcellus is up here. It's the most thermogenic, and these things also produce there's some question of whether you can use the trilinear diagram to show whether these things are background or whether they're actually real gas that escaped. And so, typically, if you're looking at this area and you have thermogenic gas, then that shouldn't be there. But if you have sodium chloride type water, some of it could be derived from native formations that are on the way up. So with that, I guess I'm 1 minute over. So this is Aerostar would like to thank you for having me here. And I guess what I'm saying, when you get your degree, or if you're an intern, send your resume to me, okay? And that you can write this down or photograph it, take a picture of it with I'll leave this up so you can take a picture of it with your phone. And Aerostar is an 8A firm. We do all this PFAS work, and we also do some EOD work, which is looking at explosives and sampling for those. What's nice about the 8A firm is that we don't have to compete against big engineering firms, and we don't have to worry as much about utilization, which is the ratio of billability to client billed work, and we don't have to compete necessarily against 30 different engineering firms. So we do have plenty of work, and we're interested in people that do data validation, people that can sample, people that can set drill rigs, people that can do GIS, especially 3D modeling like what you saw here. All those kinds of things are the hot topics now. And some groundwater modeling too. Groundwater modeling went out the window like 20 years ago, because they came up with these idea about in situ treatment, where you could just get rid of solvents by putting a heavy oxidant in the formation. But now the PFAS, they're using pump and treat techniques again, so groundwater modeling is becoming more prevalent. So with that, I'd like to thank everybody for coming here and listening, and hopefully you got a good idea about what a groundwater hydrologist just does in consulting.